All right, our last lesson of the year. So here in 11.5, we're going to start looking into yet another way to calculate probability. But today's is more specifically about independent, whoop, that's really big, 2 seconds, independent and dependent events. This is kind of that probability you would use if you wanted to, like, the probability of winning the lottery. Because what's happening is multiple things are being drawn and you want them to be drawn together. Each event in its own has its own probability, and because of the fact that you would like to have them in a group, you would try combine those separate probabilities in a specific way. So before we get too far, let's determine how we determine if two events are independent or dependent, and then we can move into actually calculating the probability. So first, let's start with independent. So two events are considered independent if the occurrence of one event does not or doesn't affect the occurrence of the other. Conversely speaking, we are dependent if it does affect the other event. All right, so let's look at some of these wordings. I'm going to circle them in a green, and then we can determine if we think that wording means dependent, independent. I'm just going to use a little D and an I to represent which one it is. So a jar contains red and blue marbles. You randomly choose a marble from the jar and do not replace it. Then you randomly choose a second marble. So we have two events happening here. We're picking a marble out. We leave it out of the jar and by not replacing it, and then we choose a second. So the big words here that are going to lead us to whether this is independent or dependent is do not replace. And then in this particular case, we would say that these two events are indeed dependent on each other because the probability of the second event is affected because there's one less marble inside of the bag. So the total value on the bottom would change. All right. A dresser drawer contains one pair of socks with each of the following colors. Each pair is folded together in a matching set. You reach into the sock drawer and choose a pair of socks without looking. You replace this pair and then choose another pair of socks. All right, so again, off of that same wording, our second probability, that's weird. Our second probability is not affected by our first probability because we put the first pair back. So we're going to say that these two events are indeed independent. So that's one wording we can look for. Did it get replaced or did it not? All right, next event, landing on heads after tossing a coin and rolling a 5 on a single 6-sided dice. So here we're dealing with a coin and a 6-sided die. So one thing to look out for when you're determining independent or dependent is, do they even come out of the same sample space? In this particular case, that answer is no. So since the outcomes of a coin are different than the outcomes of a dice, then we could say, all right, these two events are independent of each other. All right, a card is chosen at random from a standard deck of 52 cards without replacing. You pick another card. So that is going to be a dependent event. Mrs. Burnett needs 2 students to help her with a science demonstration for her class of 18 girls and 12 boys. She randomly chooses one student who comes to the front of the room. She then chooses a second student from those still seated. So I think the best wording of this would be those still seated, meaning the student she selected first did not get replaced. So these events would be considered dependent because our second probability is affected since our total number of students has lessened by 1. All right, choosing a 3 from a deck of cards, replacing it, and then choosing an ace. Again, we've replaced the card, so our sample space has not changed for our second probability, thus leading us to an independent result. So again, not only is this a good way to determine what it looks like for independent or dependent, but it also tells you that this is slightly different than what we've been calculating before for probability, because these are separate events that are occurring. It's not just two events that we want to combine together for one draw. We're drawing something, finding out the probability of that, and then drawing something else for a second event, and we could even do more than that. So independent and dependent events have what we like to call a conditional probability. Which comes with more notation that you need to be aware of. So when we have a conditional probability, we state that our second event B is the probability we want to find. However, we place this line in, and then we put whatever the first event was. The way you read this is the probability of B given that A happened. So when you find these independent or dependent, so I should say more dependent events or dependent probabilities, or you assume event 1 happened. So if you have some lucky numbers eventually when you maybe do the lottery, you need one ball to be drawn, and then to find the probability that the rest of your numbers are chosen, you're going to assume that your ball was drawn. So you have the probability of B given A occurred. So that's kind of how you read this. See, it's going to dodge a little bit. Running out of space. Writing on the edge. Whew, we got to fit. All right. So that's how you read. Let me kind of do this part again. That's how you read this notation. The probability of event B given that event A happened. So that's conditional. Now, really this conditional probability is only going to affect us in independent events, I said that wrong. In dependent events, because in independent events our second probability isn't related to our first. Thus, we have nothing that's conditional because the two have separate outcomes. Or we've replaced something so the outcome or our sample space has not changed, nor has our favorable. However, in dependent events, either the favorable, the total, or both have changed. Thus, we have a conditional probability. So let's define these so you know what they look like. And again, these formulas are going to play into some of your homework because, again, they don't always give you context behind the probability. They just give you numbers sometimes. And the biggest difference today is that you're going to know you're dealing with independent and dependent events because of instead of an or, you're going to have an and. So I want to know the probability that event A happens and then event B occurs right after that. If they are independent of each other, you will find this probability by taking the first event's probability and multiplying it by the probability of the second event. Now, if these events are dependent on each other, again, you're going to notice that they want to find the probability of A and B. So we're still working with and. Again, that's telling you what type of probability you need to find. However, to find it, you still just find the probability of the first event, but then you change your second probability to be conditional based on the result of the first probability. So in 11.4, we dealt with compound events when we added together because it was a single occurrence of drawing a number or drawing a marble or something, and we increased the favorable, so we added those together. Here we're looking for multiple occurrences to happen back to back, Thus, we're looking at independent and dependent. All right, so here we have a spinner. It has numbers on it. We would like to find the probability that you spin a 25. So event A is a 25. And tells us we will figure out that result, and then we're going to find the probability of a separate result happening right after on a second spin. Now, if you're trying to determine independent or dependent, on a spinner, if you spin a space, the space doesn't disappear, it still exists. So these should be independent of each other, because the probability of our second spin should not be affected by the probability of our first. So let's go ahead and calculate. First, we want to know the probability of our first spin equaling 25. So if we look over on our spinner, we have two spaces that are 25, so our favorable is 2 out of a total of 8 spaces. So the probability of our first spin being 25 is 2 out of 8. All right, then the probability of our next event. So now we want to know the probability that our second spin equals 50. So if you look on your spinner, only one of the spots has a 50 out of 8. Since this problem had an and, we know that we want to multiply these two things together. So the probability that we get 25 and right after that we get 50 is 2 times 1, which is 2, over 8 times 8, which is 64. Again, anytime you're giving probability, you can go as a simplified fraction, which in this case is 1 over 32. A decimal, which is 0.03125, or percent, which is 3.125%. You will notice in independent and dependent probabilities, a lot of these probabilities are going to be very small because the likelihood of things happening over and over and over again in a specific order makes it less and less likely the further you go. So there's a probability of an independent event. All right, so now let's focus on a dependent event. So you have a bowl of grapes, 36 green, 14 purple. You randomly choose one, eat it, and don't put it back. So this eat it part is telling you that we have this is kind of the same way of saying not replacing. All right, so the events are very detailed here, nice and clear. So event A, we want to pick out a green grape out of the bowl. So the probability of a green grape, I'm going to use my So they tell us that there are 36 green. They don't tell us the total. However, we could find it out by just adding 36 and 14. So probability of green should be just 36 out of 50. So there's the probability of event A. Now, we have a conditional probability. So let me write this in so you can kind of see how this looks. We ate that grape. It is no longer in the bowl. So we still want our second grape to be green. However, we are going to take into account the fact that our first grape that we ate was also green. So we immediately know, since these aren't independent, they are dependent on each other, that the second event has to be conditional. So this is how it would look if we wrote it out. So, favorable. There were 36 green grapes, but we took one out and ate it. We're assuming that happened. So now our favorable is actually only 35 green grapes. And again, since we ate the first grape, we no longer have 50 grapes in the bowl. We only have 49. So this is a situation where the conditional probability actually changes both the favorable and the total. That doesn't always happen. Sometimes it's just the total. All right. We're going to multiply because there's an and up here. So and tells us that we're multiplying. And we should get the combined probability, if you multiply straight or crossed, as 1,260 over 2,450. If we simplify that down, our answer would be 18 out of 35, which is 0.514 or 51.4%. All right. So there you've seen independent and dependent events. All right, so last but not least,